Hi, and welcome to Codex. Today we are happy to have Michael Perlmutter, who is a Hedrick Assistant Adjunct Professor in the Department of Mathematics at UCLA. Dr. Perlmutter's research focuses on problems in data science, probability, and harmonic analysis, in particular geometric deep learning and phase retrieval. Today he will be speaking on group invariant scattering. Take it away, Mike.
Hello, everybody. Thank you very much for the introduction. It's great to be back in the Codex seminar. Today, I'm going to be talking about the scattering transform and its invariance properties on graphs, Riemannian manifolds, and some other measured spaces. So I'll begin by introducing the Euclidean scattering transform, a wavelet-based model of convolutional neural networks introduced about a decade ago. Then I'm going to talk about some more recent work that I've been involved with, generalizing it to graphs and to compact Riemannian manifolds without boundary, and more recently, some generalized measure spaces. Then I'm going to discuss some applications towards efficient solutions to combinatorial optimization problems, drug discovery, and the analysis of single cell data. And then motivated by this last application, I'm going to then return to a little bit more theory, where we talk about methods for implementing the manifold scattering transform from finitely many data points. So to begin with, the scattering transform is a model of convolutional neural networks. And the primary difference between this and other CNN type architectures is that it does not use filters which are optimized from training data. Instead, it uses a pre-designed network consisting of wavelets. And what this does is it separates out the different aspects of deep learning, and it allows one to study the architectures which are used in deep learning models in isolation from the need to solve complicated optimization problems. And what this does is it highlights the symmetries of the networks with respect to certain group actions. Worth noting that the name of this paper was a group invariant scattering, which if you were at Codex a couple of weeks ago, you may have heard of a recent paper that came out called Group Invariant Max Filtering, which again is getting on some of the key insights, which is that there's really a fundamental role played by symmetries to group actions in designing effective machine learning algorithms. So the advantages of the scattering transform is, one, it has provable stability and invariance properties. Two, it's also a practical object in certain situations that can get very good results. And it's much less data hungry. CNNs have emerged as all of the rage, but one of the limitations of them is that they need lots of data. Scattering is an alternative if you don't have very much. So when I say scattering is a model of convolutional neural networks, I need to be careful with what I actually mean. And in order to explain that, I want you to put in your brain the example task of distinguishing cats versus dogs. So pretend you have a data set of lots of cute little cat pics and a bunch of doggies, and you want to develop a machine learning model that can look at a new image and figure out, is this a cat or a dog? The state-of-the-art methods for solving these problems are deep neural networks in general, or convolutional neural networks in particular. And these can be thought of as consisting of two halves. There's an embedding, or a front end of the network, which creates a hidden representation of each input in some sort of high dimensional vector space. And then there's the back end, which actually makes the final prediction based on this hidden representation. So when we say scattering is a model of CNNs or of neural networks, we really mean it's a model of this front end, the embedding step, the hidden transformed representation. So if you want to use the scattering transform, like for a task such as image classification, what you do is you first transform the image with the scattering transform, and then you apply whatever your favorite traditional classifier is, where in this picture, I'm showing an example of something called a support vector machine. Now, the key object that the scattering transform is based on is the wavelet transform. And this may be familiar to many people in the Codex audience, but for people who have not seen it before, the ingredients of this would be a mean zero function, psi, and a non-negative scaling function, phi, which integrates to 1. Then we consider dilations at dyadic scales of both of these functions, and we consider the associated convolution operators with these dilated mean zero functions and dilated scaling functions. We call these the wavelet coefficients, and we think of this as a low-pass filtering because it tends to smooth out or blur an image. And the idea is that when you dilate these at different scales 2 to the j, you're trying to capture information about your input, say, image, at different scales of resolution. Or it's a well-known fact that when you dilate an image in space, you are also dilating it in the Fourier or the frequency domain in the opposite direction. So you can also interpret these different WJs as focusing in on different frequency bands if you like to think about things in the Fourier domain. And generally speaking, these wavelets are constructed in such a way with psi and phi fitting together nicely, such that the wavelet transform as a whole is going to be an isometry. Meaning if you take the energy of each of the wavelet coefficients plus the response to the low-pass filter and add that all up, then you'll get the energy of the original signal. Now, these have been widely applied to images. And one of the reasons why is that many natural objects tend to be sparse in the wavelet basis, or in this wavelet representation produced by the frame. It's a frame, not a basis. So here what we do is we have a picture of a man riding a horse, and we take its wavelet transform, and we can see that this wavelet transform is nearly all 0. But we can still see the important details of this man on the horse. And this will allow us to store this image in a compressed format on a computer because most of the information is zeros and you don't need to store that. But given this sparse representation, we still have enough information that we need in order to reconstruct an image. And so because of this, these have been really widely applied in image processing and are part of the reason why you're able to store images on your phone in a data efficient manner. For example, this article right here actually does a nice summary of wavelets in image processing from the New York Times from last year. And also, for people in the audience who have not seen this before, this is a bit of an inside joke in the applied math and computer science community. So if you'd like to know more about the important role that muscular shirtless men on horseback have played in the history of applied mathematics, you can learn a lot more about the surprising history here, or here when I post the image. Or sorry, when I post the slides. But moving on from Mr. Lenzoni, the scattering transform is essentially a multi-layered cascade of wavelet transforms intermixed with nonlinearities. In particular, it's composed of many wavelets stacked on top of each other, which is what leads to the term of deep learning, because it's this layer stacked on top of this layer, stacked on top of this layer, etc. And each layer is first a wavelet transform and then a nonlinearity. Then for a scattering path, P equal J1 through Jm, you take this operator Uj and you apply it iteratively at these different scales. And this is what we call the U operator. And then given this U operator, you actually do one of two things. And this is something I want to emphasize because this is something that tends to get lost in discussion around the scattering transform, is there's essentially two different versions of the scattering transform. There's what's called the windowed scattering transform, where you take this U and you apply a low pass filter. And then there's the limiting object as J goes to infinity. And this is essentially going to be equivalent to taking the L1 norm of the U up to some unimportant renormalization terms. Or well, they're important, but not for our discussion here, I should say. And the reason the scattering transform was to introduce was to understand symmetries to group action. And what you can prove is that if you have a translation operator, TC f of x is equal to f of x minus c, that the windowed scattering transform is going to commute with these translation operators. This is a term which is popularly referred to as equivariance, meaning that if you translate an image and then take the scattering transform, it's the same as if you did those two operations in the opposite order. On the other hand, the non-windowed scattering transform is invariant, namely that if you translate an image, the hidden representation here is not going to change. And indeed, these invariants and equivariants are fundamentally related. This is something that Emily actually brought up a couple of weeks ago in the Codex seminar. is that there's a kind of a blueprint for extracting invariance from equivariance. Namely, the operator U is also going to be translation equivariant. Then the non-windowed scattering transform is the L1 norm of the U operator. And the L1 norm is translation invariant, just to do a simple U substitution. And if you use these facts, you can verify, it's a nice little exercise to verify that this then implies that the non-windowed scattering transform is translation invariant. And indeed, this is a widely used formula, which is deeply involved in the proofs of Malaz's theorems. And it's been recently referred to as the blueprint of geometric deep learning. And if you want, you can go to the website geometricdeeplearning.com, which this is an excellent resource for two reasons. One, several of the leading researchers in this field have created a free proto book that really explores all these concepts in great detail. And something that I like even better than a free proto book is they also have a 12-part lecture series consisting of 1-hour lectures where they really explain all these topics in excellent detail. So if you like my talk today, I encourage you to check that out. So I'm going to further motivate the role of both invariance and equivariance, and I'm going to claim that these are both important things. I think a lot of the time the discussion focuses on invariance as being the real star of the show and equivariance as being this kind of intermediate means to an end. But I'm going to claim that in different tasks, one of these is important or the other. So if our goal is to figure out whether or not the eyes are open, what we want is a single representation of the entire image, which is unchanged by moving around the face, because that doesn't change whether or not the eyes are open. On the other hand, if you want to find the location of the eyes, then you would want to have a hidden representation of every pixel. And if you slide the image around, you'd want that hidden representation to move the same way that you're moving the image. On an offhand note, I recently had to get an MRI done because I got some back pain. And these exact same applications would be arising in the context of medical imaging. If you're looking at, like, say, a CAT scan or something, and you want to figure out, is there an abnormality? That's like the question of, are the eyes open? You want an invariant representation. Okay, say you go to the doctor and they say there's something wrong with you. Well, the next thing you're going to want to say is, well, what's wrong with me? You'd want to find the location of the abnormality. And that's a direct parallel to this question of where are the eyes. So the other main theoretical insight from the scattering transform is, why is a deep multi-layer nonlinear network better than just like a really big linear transformation? And the answer is that a linear network can be either invariant or sufficiently descriptive, but it's very hard, if not impossible, for it to be both. And to illustrate this point, you could consider taking a global average. This is going to be perfectly translation invariant. Again, that's a simple U substitution. But if you think about this in the frequency domain, you see that this is the 0th order Fourier coefficient, which means you're throwing away high frequency information. Conversely, you can use wavelet filters to capture high frequency information, but these are going to be unstable to translations. And so the intuition behind the scattering transform in specific and deep networks in general is that you're able to first capture high frequency information using, say, the wavelets, and then the modulus somehow pushes this information down to lower frequencies where it's going to be more stable, and therefore this whole network provides a way of stably capturing high frequency information. More specifically, Malaz is able to prove the following theorems: that the scattering transform here is going to be non-expansive. In other words, it's continuous on L2. Also, it's going to be invariant to translations and stable to small deformations. So here we have a deformation model, f of x minus some tau of x. If tau is a constant function, this is exactly a translation. And in that case, these two terms here would go away because the gradient of a constant function and the Hessian of a constant function are both 0. And all you'd be left with is this term here, which would go to 0 in the limit where we get the non-windowed scattering transform. And this is what's referred to as Malaz type stability results, which again are something which is analyzed in the group invariant filtering paper. Another thing which is worth noting is even at a finite scale, we have an equivariance result like this, where again, there's a quantitative bound on how much it'll matter if you take the scattering transform, then deform it, versus doing these things in the other way around. This is something that follows from the proof of lemma 2.12 in Malah's paper. It's not actually stated there, but if you look at the first proof, the first thing he does is he separates out this commutator term from this term here. And then the proof is based on proving this and then applying the triangle inequality. Theorem 2.14 of Malah's paper is a result similar to this, but it's focusing on a single wavelet coefficient. In any case, that's the theory of Euclidean scattering. So before I pivot to geometric deep learning, a couple example applications, which I'm fond of. One is low data environments. So here what we have is we have a bunch of unexploded bombs on the surface of the ocean floor. And these would be fairly simple for a computer vision algorithm to recognize. The problem is that this is not what they look like when they're on the ocean floor. When they're on the ocean floor, they look like this. And additionally, we don't have a massive data set full of millions of unexploded bombs on the surface of the ocean, thank goodness. But nevertheless, scattering is able to be effective on a data set of 14 images. And what's particularly noticeable about this is the alternative in a low data environment is something called transfer learning, where what this means is that you have a small data set and you can't train your model. So you said you take some big data set, you train your model on the big data set, and then you use it on the small data set. In other words, you transfer your learning. Transfer learning works well if you have a good thing to transfer from. So if you have if you want to go, train a new CNN and apply it to photos of your cat, you can train it on a bunch of photos of cats on the internet. Unfortunately, fortunately, there's not millions of photos like this on the internet. So there's really not a good candidate for transfer learning, but scattering is still an effective tool. The other thing about having a designed network is you get to design the network. And in particular, if you have some physical intuition that you want to build into this design, you can do so. So this is a project which was some of my former lab mates at my old job at Michigan State. They were collaborating with material scientists on a problem related to lithium and silicon molecules. And they know the underlying physics is the Schrodinger equation. And so what they do is they use wavelets, which closely resemble the solutions to the Schrodinger equation. And this allows them to produce an invariant representation, which is interpretable to the domain experts. So that was the background portion of my talk, focusing in on the Euclidean scattering transform. I should emphasize that everything so far in the talk is the work that other people have done, except the poorly done wavelet transform on Fabio. I did do that in Python last week, but that was using pre-designed tools. But everything going forward is going to be more projects that I was involved in. In any case, geometric deep learning is a new field that wants to say, wow, CNNs have had this tremendous impact on things related to computer vision. You can, take a photo of the beach and then later go onto your phone and say, show me photos of the beach, and it'll pull that photo right up for you. Wouldn't it be great if there was other data sets where these same tools were effective? And in particular, it focuses on things like graphs and manifolds, which are natural models of, say, molecules or surfaces that appear in computer vision. So some examples of the tasks that we're interested in the graph setting, there's maybe 2 or 3 main family of tasks. One is node level tasks. So you can picture you have a social network, you know the political affiliation of some of the users, you know who's friends with each other and stuff like that. Maybe you have some information about every user, and you want to predict the political affiliation of the other users. And something important to note, for node level tasks, you're typically speaking going to want an equivariant representation, not an invariant representation. Because if you reorder the vertices of the graph, you would want to reorder your hidden representation in the same manner. On the other hand, there's also graph level tasks. And so a classic example of this is graph classification. You got a data set of carbon molecules. Some of these are known to be associated with lung cancer. Others are known not to be associated with lung cancer. And what you want is a predictive model that can determine whether some new molecule is something that cancer scientists should be doing research on, or whether or not it's probably safe. Another example problem is graph synthesis. So here what it is, we got a big data set of molecules that are known to have, say, drug-like properties. And we want to say, hey, here's an example of a new molecule which looks like it was from the original data set. All of those molecules from the original data were things which were useful. So maybe you should try synthesizing and doing research on this new molecule as well. Now here, if you reorder the vertices just by renumbering them, nothing actually happens in physical space. So you want a representation which is going to be invariant. So that's some motivation. Now getting to the actual math. The way you can extend convolutional networks to graphs and manifolds is recalling the fact that in the Euclidean domains, convolution corresponds to pointwise multiplication in a Fourier basis, or inside of a Fourier transform. So in the general setting, you let L either be the Laplace-Beltrami operator on a compact Riemannian manifold without boundary, or another matrix called the graph Laplacian. You consider an eigenbasis, such that L phi k is lambda phi k. And then a spectral convolution operator is any operator which first expands a function in this generalized Fourier basis, and then does a pointwise multiplication inside of this sum. And indeed, this is the notion of convolution that's used in a lot of popular graph neural networks, such as ShebNet or KaliNet. But in order for the network to be guaranteed to have the stability and invariance properties one might want, especially in the manifold case, we actually need an additional assumption, which is that hk, the filter tap, is actually a function, which I'm also going to call h in a slight use of notation. It's a function of the eigenvalue. And what you can then prove is that if you have this assumption, then your filtering will be equivariant with either with respect to isometries of the manifolds or with respect to permutations of the graph. In other words, if you filter, then rotate, that's the same as if you first rotate and then filter. Notably, this assumption is at least sometimes necessary, and there's actually quite a simple counterexample, which is if your manifold is the circle and you rotate it 90 degrees, you change all sines to cosines and cosines to negative signs or something like that, and therefore you don't actually get an equivariant representation. Now, we're going to be interested in a specific set of spectral filters associated to heat flow, where we're going to consider a heat type equation where we've got a function u of xt such that its time derivative is equal to its spatial Laplacian, and its initial data satisfies f of x. And we're going to have pt to be a family of operators such that pt f of x is equal to the solution to this differential equation. Now, it's well known that this has a spectral representation. PTF is equal to e to the minus t Laplacian f of x. And indeed, if you're willing to be mathematically informal, you can just actually take the time derivative and verify that this works. And you can also, when I say it's e to the minus t the Laplacian, what I actually mean is that you're writing it as you're raising each of the eigenfunctions by a filter tap e to the minus lambda k t inside of the sum. Now, the reason why this is useful is that intuitively, heat diffusion is a geometric descriptor. In other words, if you have two curved spaces with different shapes, heat's going to spread out through them differently. It's also worth noting that there's a probabilistic interpretation, namely that the semigroup is equal to the expected value of f of a Brownian motion started from a point x. So given this heat semigroup, we're then going to define spectral wavelets, which are defined by taking the heat semigroup at two different scales, and we're actually going to take a square root of them. And in order to take the square root of a linear operator, we use the fact that it can be written out in the spectral domain, and we do the square root inside of the sum. And you can verify that if you apply this operator twice, the square root twice works the way that it should. The theorem, which you might have been able to guess, is that this generalized wavelet transform is still going to be in isometry, and it's still going to preserve the energy of the original signal. I should also know that this is closely based on several other wavelet constructions, including some diffusion wavelets produced by Koifman and Maggioni a couple of decades ago. Euclidean wavelets, I said one of the goals was to capture information at different scales of spatial resolution. This same interpretation holds here, where here we've got a wavelet at a small scale, and as we go from left to right, it gets more evenly spread over the surface of our manifold. Now, the annoying thing about square roots is that if you want to implement that formula, you do have to actually compute all of the eigenfunctions and eigenvalues and things of that nature. And this can lead to some computational problems. So it's also worth considering a modified version of this, which we're going to call W2, where W2 it's exactly the same definition, except there's no square root. So it's heat diffusion at two different time scales subtracted from one another. Again, this can be written as a spectral representation. And here I'm actually writing out to the first power, which is a bit redundant. But I really want to emphasize that if you change this 1 to a 1/2, this is exactly the formula from a couple of slides ago. And we're again able to prove a theorem about this frame, but it's a little bit weaker than before. The price we pay for computational efficiency is that we no longer have an isometry. You can't always get what you want, but we're still able to get something. And we're able to get that it's a non-expansive frame, which means that we have a quantitative bound that's independent of any of these parameters. I believe it is actually a 0.08, but I haven't looked at it in a while, where you're guaranteed to preserve a certain fraction of the energy. Now, when we're on graphs rather than manifolds, it's a little bit simple. We can actually do something a little bit simpler. So on a manifold, the heat semi-group's a model of Brownian motion, a particle continuously wandering around a continuous space. The natural analog of this on a graph, there is such thing as the graph heat semi-group, but the most natural or most widely studied analog is the random walk. So we just let P be the transition matrix of a person who's just randomly stepping from one vertex to any of its neighbors, which I mean the ijth entry is the probability that you move from vertex I to vertex j. And then we just power this to two different scales of diffusion and subtract. And what's noticeable about these wavelets, as opposed to the filters which are used in a lot of other graph neural network architectures, is that if you let a random walker move for 2 to the j timescales, it's able to see a radius of 2 to the j, which means it's able to capture long-range interactions or the global structure of your network. By contrast, a lot of popular graph neural networks, they're very much heavily based on localization. In other words, I'm going to try to identify who is Dustin by looking at all of his neighbors and his immediate family, but not looking at his distant cousins. In any case, whatever your favorite definition of the geometric scattering transform is, of the wavelet, the geometric scattering transform can essentially be defined in the same way as before. It's you do an alternating sequence of wavelets and moduluses or absolute values. And then you can apply a low pass filter to obtain a windowed scattering transform, where, by the way, the term windowed means that a low pass filter is taking an average within a certain radius, like within a certain window. The non-windowed scattering transform can be defined as the L1 norm of the U operator. And also, at least in the manifold case, this can be written as integration against the bottom eigenfunction up to a normalizing constant. And the proof that these two things are equal up to multiplication by a constant is simply due to the fact that the bottom eigenfunction is constant, and integrating against a constant function is equivalent to taking the L1 norm. There are similar definitions and results for the graph scattering transform. So theoretical guarantees. This result here is the same as before. The scattering transform is non-expansive, same as in the Euclidean case. The windowed scattering transform is going to be Lipschitz continuous with a constant depending on the manifolds. This constant actually is equal to 1, but in some later results, it'll be a not 1 constant. So I'm just putting it here to kind of preview where I'm going. Oops, sorry. Also, the generalization of translations in the manifold setting would be the action of isometry. So there would be a composition operator associated to an isometry, which we view as a generalized translation operator. And analogously to the Euclidean case, you can check that the windowed scattering transform is equivariant, the non-windowed scattering transform is invariant, and the windowed scattering transform is a limit. You can also produce a stability result for almost isometries and derive similar results for graphs, where instead of isometries of the manifold, you'd be looking at permutations of the vertex set. So that was some work which was a couple of years old by now. And so what I'm going to talk about for the next second half of the talk is, can we go further? And both graphs and manifolds are metric measure spaces, and most of the ideas behind graph and manifold scattering are quite the same. So the question is can we generalize these themes further to more general spaces? And both graphs and manifolds are metric measure spaces. And so the first question we should ask is, which of these properties is important? Is it the matter that it's a measure space or a metric space? So the word measure space appears in the title of my talk, so I kind of gave away the answer. But I will claim that at least when we started working on this, this was not obvious until we actually started working on it for a while. Another question is, in general, what groups should things be invariant to? And so that's what I'm going to talk about. And this is all going to be joint work with a couple of Codex alums, Deanna Needell and Hao-Ting Wu. Also several other mathematicians, Joyce Chu, Matthew Hearn, and I think that's everybody. A couple of computer scientists, Smitha Krishnaswamy and Siddharth. And Holly Stage is actually trained as an immunologist, which will be important when we get to some applications later. Holly also made the animation with the sliding faces, so I'm deeply indebted to her on that front as well. In any case, our generalized setup is we have a measure space, xf mu. We have our generalized Laplacian type operator, which we're going to call L. It's assumed to be positive, semi-definite. There wasn't room on the slides, but it is required to have a spectral gap, meaning that its second eigenvector has to be strictly positive. We assume we have an orthonormal eigenbasis, and we define the heat semigroup as e to the minus LT. Then we define wavelets the same manner as before. The heat semigroup at 2 different time scales subtracted from one another. And then the low pass filter is the heat semigroup at a large time scale. And you can probably guess what this proposition is going to be because it's the same as before, but on a general measure space. This wavelet transform is still going to be a non-expansive frame. Then definitions of the windowed scattering transform is again just the same as it is in the manifold scattering case. Wavelet nonlinearity, wavelet nonlinearity, wavelet nonlinearity, low pass filter. For the non-windowed scattering transform, it's integration against the bottom eigenfunction. In the manifold case, I said this was the same as taking the L1 norm up to a constant. That is no longer true. In general, the bottom eigenvector is not going to be constant. And indeed, even in the graph case, if you were, say, looking at a weighted measure, which one might reasonably want to do to give more importance to vertices with high degree or low degree or something like that, or even if one wanted to use the normalized graph Laplacian rather than the unnormalized combinatorial graph Laplacian, then these two definitions would not be equivalent. So this is the one where this is the appropriate definition of the non-windowed scattering transform, which allows you to generalize the theoretical results. And then given the non-expansiveness of the wavelet operator, it's then fairly straightforward to prove that the scattering transform is going to be non-expansive. The windowed scattering transform is going to be Lipschitz continuous. Sometimes this constant will be equal to 1, but other times it'll be a bit greater than 1. For example, if you're using the normalized graph Laplacian, this constant's going to depend on the ratio between the highest degree vertex and the lowest degree vertex, for example. And the next thing we want to consider is what group should we be invariant to in this general setting? And the first guess would be, okay, suppose we have a family of composition operators acting on the set underlying our measure space. Then, well, if we want it to be a measure space preserving structure, maybe we want a map that if you apply it to some set B, the measure doesn't change. At least to me, this was the obvious first guess. And this turns out to be maybe 80% wrong, because this is actually way too strong of an assumption. Oop. Somehow that went right to the end of the slide. Hope you enjoyed the second half of my talk. Okay, okay. So the problem is, what if you have a weighted measure on a graph? Where again, you might want to weight the important nodes of your network, where like that's the most important user on a network or something. And this will not be, this preservation of measure will not hold in this setting, not at all. Sorry, I don't know what's happening with my jumpiness. So instead we have the weaker condition that the group induces an isometry on the associated Hilbert space. And this is, in other words, if you perturb F and G and you take their inner product, that's the same as if you didn't perturb them. And you can verify that this is a property satisfied both by the isometry group on manifolds and also by the permutation group on graphs. And this is a much weaker condition than preservation of measure in general. And so the first theorem we're able to prove is that under this general setup, this will likely sound familiar, the windowed scattering transform is going to be equivariant to these group actions, and the non-windowed scattering transform is going to be invariant. Now, the next question you'd ask is, well, is the windowed scattering transform invariant in the limit? And the answer is sometimes. So now here we again need the assumption we're preserving inner products. We also need preservation of measure now. And we also need the assumption that phi0, the bottom eigenfunction, is constant. And I am missing an is equal to 0 here. But in this case, we're going to get invariance in the limit. So we have three assumptions. So this sounds like a kind of a strong theorem. And so it's worth noting that these assumptions are satisfied by the Laplace-Beltrami operator on a compact Riemannian manifold, by the unnormalized graph Laplacian on a graph with the unweighted measure of the vertices. But also importantly, they're not satisfied on some natural settings, such as just a graph with the simple unnormalized simple unweighted measure, but you're using the normalized graph Laplacian. So examples of set spaces which are fitting within our framework: traditional graphs with the graph Laplacian, degree matrix minus adjacency matrix. Degree matrix is a matrix that keeps track of how many friends each person has. A is a matrix recording a ledger of who is friends with whom. And you can also use normalized variations of the graph Laplacian. And something which is worth noting, you can use any three of these normalizations where you either normalize in a symmetric manner or on the left, on the right. But if you do, you have to pick your measure differently in order for this to be a self-adjoint operator on your measure space. Other example is, of course, manifolds with the Laplace-Beltrami operator, or in general, you could consider some other elliptic differential operators defined on your manifolds. Some examples not considered in previous literature on the scattering transform, though, we have directed graphs. On a directed graph, the straightforward extension of the magnetic Laplacian is not going to be the straightforward definition of the graph Laplacian, D minus A, is not going to be self-adjoint. But there's a different matrix called the magnetic Laplacian, which is. Similarly, on a signed graph, d minus a is not going to be positive definite, but there's a different matrix called the signed Laplacian, which is. And if you're given these two examples and you want to put them together, say you have something like influence on a social network, and Emily influences me in a positive way. I don't influence Emily, but I do influence Dustin, but I influence him in a negative way. We want to have signed and directed graphs. And so the magnetic and the signed Laplacian are things which have been around for a while. The magnetic signed Laplacian is something that my co-authors and I introduced in a recent work that was actually just put up on the archive this week. So I talked about the magnetic Laplacian extensively in my previous codex talk. Here it only gets one slide. But what you do is you take a symmetrized version of the adjacency matrix on a directed graph, where you just take A plus A transpose, and also an anti-symmetrized version of it, which we call theta. And then you construct what's called a Hermitian adjacency matrix, which is going to be the Hadamard pointwise multiplication of the symmetric part and e to the I, the anti-symmetric part. You can verify that A is symmetric, theta is anti-symmetric, at least in the case where the graph is purely directed, so there's no like back and forth links. And so what this means is that if you define the Laplacian to be D, it's the symmetrized degree matrix, minus this generalized adjacency matrix, that the undirected geometry of the graph, is there a link between two vertices, is captured by the magnitude of every entry. The directional information is instead incorporated by the complex phase. In other words, we're using polar coordinates to identify a directed graph. Is there a link? That's the magnitude. Which direction is the link? That's the phase. And this Laplacian's been around for a while, first appearing in the physics literature, but it's also been used in a graph neural network in some work that I did with Shitong Zhang, Yishuan He, Matt Hearn, and Nathan Burgone. There is also a signed Laplacian, which is again a modified version of the graph Laplacian, where now your degree matrix, rather than adding up all of the entries, it adds up all of the magnitudes of entries in a given row. And this is something which has been used by spectral clustering by Mihai Cucaringu and several other people. And so Yishuan He and I were interested in, well, can we extend this further to get this all to work together? So what we came up with was essentially what's a simple algebraic formula that satisfies the following two properties. One, if you have a graph which is signed but not directed, it reduces to the signed Laplacian. And two, if you have a graph which is directed but not signed, then it reduces to the magnetic Laplacian. And so this is what we came up with. We call it, due to creativity constraints, we called it the magnetic signed Laplacian. And we recently introduced this in into a signed directed neural network. Worth noting, both this and magnet from the previous slide, those aren't scattering. These are more standard, fully trained, highly localized graph neural networks. However, the Laplacians used there perfectly fit well within the theory of our paper. And indeed, we did some experiments with magnetic scattering, and it doesn't seem to perform quite well, at least on stochastic block models. So now I'm going to pivot from theory to applications before getting a little bit back to theory. So one of the things we want to do, scattering was introduced, the original scattering transform was introduced to increase our theoretical understanding of CNNs. Similarly with graph scattering, we initially introduced this as, here's a theoretical object that lets us understand things. And one of the great things about understanding stuff is you then use that understanding to go do stuff. And in particular, we try to use these understandings to develop highly performant networks that can solve challenging and important problems, such as combinatorial optimization, drug discovery, or personalized medicine. So our first insight was that the wavelets used in scattering, they're different than what's used in traditional graph neural networks. What traditional graph neural networks did, I talked about this a lot in my other codex talk, I haven't really gotten into it today, but they really rely on looking at localized averages of trying to figure out, if you're a user in a social network, you're probably pretty similar to your friends, and we're going to try to produce a hidden representation of you, which is somehow quite similar to most of your friends. And can be thought of as promoting smoothness, trying to make it not vary so much when you move around a localized neighborhood. But the problem is that you can have too much of a good thing, and you can lead to a problem called oversmoothing. And if you filter the data multiple times the way that you do in a typical GNN, you really oversmooth the data. And so the way that you avoid this is typically most graph neural networks only use like 2 or 3 layers, but this creates this new problem, underreaching. You can't incorporate global geometry, you're only looking at localized neighborhoods. Now, scattering uses a single wavelet filter bank that is focusing in on different frequency bands, so it's able to overcome the oversmoothing problem, and it also has a wide receptive field, so it's able to simultaneously not suffer from underreaching. Whereas with GNNs, if you want to go deep, they typically use localized filters. So if you want to go deep enough to incorporate long-range interactions, you're really going to be plagued by severe underreaching. So that was all a lot of air math, but the point is that scattering in more traditional GNNs, they do good stuff and they do different good stuff. And so to get the best of both worlds, we'll take them both. In other words, we build a hybrid network that incorporates both ideas from traditional GNNs and wavelets like used in scattering. And in principle, you'd have to pick, okay, how many wavelet filters do I want versus how many traditional filters do I want? But we're able to automatically balance that using an attention mechanism. And we are actually able to scale this up to large data sets, thanks to some previous work, which was also aiming to incorporate learning into the scattering framework, where there's a fast and efficient implementation of the graph scattering transform, where essentially what makes it fast is that you never need to form a dense matrix, and everything can be done via sparse matrix vector multiplications. So like I said earlier, the thing about most GNNs is they try to make you very similar to your neighbors in your hidden representation. And this works well in some settings. If you're trying to predict Republican versus Democrat, most Republicans are friends with a lot of other Republicans. Most Democrats are friends with lots of other Democrats. But there's other problems where this is not the right framework. So the max click problem is you have a big graph and you want to find the largest fully connected subgraph within the graph. And an important part of this is you need to be able to distinguish who's somebody who's not in the click, but is friends with most of the members of the click. In other words, who are the borderline candidates? How can we kick them out? So you need a discriminative representation that's not nearly smooth. So visually, here's the representation produced by the scattering transform, and here's the representation produced by a traditional graph convolutional network. And indeed, we're able to see that our scattering-based method is more accurate than other GNN-based methods and is faster than other combinatorial solvers, which there are ways where you can solve this by brute force, but getting exact solutions is quite challenging, and indeed, this is known to be an NP-hard problem. The other application which we've used this for is drug generation, molecular generation. So here what we have is we have a complicated network where we first take scattering coefficients, or here we actually use something slightly different called scattering moments. And then we train several neural networks on top of the scattering and then another neural network on top of that. I'm not going to get too much into the details of this because there's a lot of different pieces to this architecture. But the point is the front end is scattering. And the reason why scattering is useful is for molecules are not like social networks. You really do need to have the global structure in order to be able to do useful things. And that's what scattering is good for. Last application, before I pivot back to theory, is single cell data. So we've got 54 patients who were diagnosed with melanoma, and we have records of whether or not they've responded well to immunotherapy. We have nearly 12,000 cells per patient, and for every cell, we measure 30 different proteins. And our goal is, okay, we've got some new patient, we did some imaging on them. We want to predict whether or not they're going to respond well to treatment. So should we do immunotherapy or should we do something else? And I think it's clear why this is an important problem. I don't think it's clear right away what the heck this has to do with geometric deep learning. And the answer is that we can formulate this as a manifold classification problem. So every cell, there's 30 measurements, so we can model this as a point in R to the 30. And then every person is a collection of 12,000 cells. So we can model every person as a high dimensional point cloud. And then we make the manifold hypothesis as a modeling assumption, where we assume that each person's points lie upon some d-dimensional manifold for some d that's less than 30. So you'd have a different manifold for me and a different manifold for Emily and a different manifold for Dustin, etc. And so this personalized medicine problem can be modeled as a manifold classification problem. And indeed, we're able to see that with a scattering-based approach, we're able to get 83% accuracy compared to 48% with baseline. But this also raises a challenge, which is, okay, we're making a modeling assumption that there's some unknown Mike manifold, but we don't know the Mike manifold. How do we actually do stuff with this? How do we actually implement things? And the answer to this challenge is to use manifold learning. So manifold learning is something which has been around for nearly 20 years now and has been widely applied to high-dimensional biomedical data sets. Some notable examples include the diffusion maps algorithm of Koifman and Lafon, or also the Laplacian eigenmaps of Belkin and Niogi. And the basic idea is that you take these points and you build a graph where the points are the vertices of the graph. And you use something called an affinity kernel, typically a Gaussian kernel, or sometimes also a nearest neighbors kernel, to build edge weights of this graph. And then you approximate the eigenfunctions and eigenvalues of the Laplace-Beltrami operator of your unknown manifold by eigenvectors and eigenvalues of the graph Laplacian. And then given that, you can then use the fact that the heat semigroup can be written in terms of eigenvectors and eigenfunctions to approximate the heat semigroup. Then our wavelets are built from the heat semigroup, so then it's straightforward to do from there. And then implementing the scattering transform is then a bunch of wavelets and nonlinearities intermixed in an appropriate manner. So the question is, does this work? Sounds good. And so the theorem we prove is yes. If the kernel is constructed properly, in particular, we focus in on a Gaussian kernel, and the sample points are drawn IID uniformly at random, and several other assumptions, then with high probability, we're able to derive a quantitative rate of convergence for these coefficients. Notably, the rate of convergence scales with the true dimension of the manifold, the intrinsic geometry, not this high dimensional space that you're embedded in. And this result builds on previous work by Chang and Nanwu. This result here was guaranteeing the result convergence of individual eigenvectors and individual eigenvalues. Notably, the eigenvectors here are converging in L2, not just in L infinity. The fact that they're converging in L2 is important, otherwise the proof does not work. And I am not going to tell you how long it took us to figure that out. But that's why we're focusing on this particular result. The other thing is that our rate of convergence with respect to n is essentially equivalent to this previous result. So we have like the same rate of convergence for these complicated scattering coefficients as with just individual eigenvectors or eigenvalues. Although the big O notation is letting us hide some things, such as the constants are a bit bigger. The other thing that's notable about this result is that it's the first of its kind for any type of neural network operator derived from the Laplace-Beltrami operator. I think developing manifold neural networks could really be a transformative technology. Graph neural networks, they're less than a decade old, and they're already used in lots of high-powered industrial applications, such as powering Amazon's recommender system or Google Maps. Manifold neural networks are much less explored. There's been some work on their stability analysis, and there's been a lot of work on the special case of two-dimensional surfaces embedded in 3D space, because that's really important for computer graphics. But by and large, this is a much less explored field than graph neural networks. And I think that if people were to develop, fully trained ShevNet style networks for manifold neural networks, one could likely use the techniques here to analyze the convergence rates. In other words, the sampling requirements of these later networks. So that's where I'm going to wrap up. In conclusion, the scattering transform is a wavelet-based model of CNNs that highlights the role of invariance and its provable stability and invariance guarantees and works well in low data environments. Actually, even drawing back to the melanoma example, you'll note that our data set was only 54 people, which again, low data environment. The scattering transform can be extended to graphs, manifolds, and other measure spaces, and the theoretical guarantees are going to be similar to the original Millar results. And the manifold scattering transform can be implemented on unknown manifolds via a diffusion maps-based approach. There's many possible example applications. Some of them are combinatorial optimization, drug discovery, and predicting patient outcomes. And that is where I'm going to stop.